But we are going to go on to some bonus C to ARM stuff. This might be helpful for the exam. So I think we have like 5 questions that we'll just breeze through here. Before we get into the ARM stuff specifically, I want to show you the similarities between LC2K and ARM. There's a separate green sheet that you can find on our website that has all the ARM instructions within like V8 that we can use. But we are going to be just going through the similarities to LC2K for now. So to start off, we have add, which is pretty regular for all ISAs. You have to have some sort of add instruction. I say have to. Technically, you don't have to, but it's pretty common, I would say. In ARM, we can also add constants instead of loading them from memory first. And then we can also do subtractions. And then finally, like I said a second ago, we can also do multiplications. And you'll see in that homework problem that Sunny was talking about, how it will technically take the multiplication pseudo instruction, which means that it really represents some other instructions, and expand it into a bunch of adds using the algorithm we just went over. And so if you see a mul instruction, that's really doing multiple adds. We have a couple others. We can do a straight up 0 out of some sort of register. We can do shifts. Those are all the things related to adds. Then we have, well, we don't actually have NOR instructions, but we have the easier or immediate, add immediate, or that's supposed to say and immediate, and exclusive or immediate. I believe all those immediates are signed, but I might be mistaken. If we want to do a straight up not, we can't do that in like V8. We could do an exclusive or with, I suppose, all ones. So if you have some register that's -1, you could do an exclusive or with -1 to get a not. But there's not a direct not instruction in like V8. Now for our loads and stores, we have multiple types of loads and stores. And that's because ARM is byte addressable. It's not word addressable. And so we can load multiples of different bytes into our registers, which are 64-bit. We can load words, which are 32 bits. And so if you see this S, that means signed. So that'll do a sign extension that we talked about earlier. If it's just a ladder W, that will zero out the upper 32 bits. But if it's a SW, it'll do a sign extension for the upper 32 bits. And I think we also have ladder SH, which does a signed half word, which is 2 bytes. And then we also have ladder signed byte. The thing is, we don't need those different types of signed and unsigned stores, because a store is just going to chop off the leading bits and preserve the last bits. So if we have, let me think, if we have 128, for example, 128 is 1 1 followed by 8 zeros. If we were to do a stir B from a register that had 128, it would actually store 0 to that byte that it refers to. And it's going to chop off all the leading things. And so that would, again, be the same as a mask with 127, which is 128 minus 1, because 128 is power of 2. So there's similar analogs for the other stores. And that means that when we load back from something that was stored, we can choose whether to do the signed or the unsigned, depending on what the variable type is. For branches, for conditional branches, that is, we have to do 2 instructions. We always have to do a compare instruction or some sort of instruction that does what we call setting flags. ARM has these separate bits or bit registers for flags. And they just store information on if 2 registers are equal, if 2 registers like overflow or negative or whatever. And so after we do the compare, then we can do a branch. And this EQ is not actually going to look at the original registers that we're comparing. It's going to look at these flag registers and branch based off that. But it's essentially the same thing. And then we also have a unconditional branch, and a branch if 0. So this CBZ, we don't need the compare instruction first for that one. We can just branch if it's 0. Jailer is a little bit different. We have branch registers. We have branch link. I wouldn't I wouldn't worry about that too much, but branch register goes to a location that is stored in a register, and branch link essentially puts PC plus 4, because it's by addressable, which is basically PC plus 1 in LC2K, stores that into a register. And I don't know if it's in Leg V8, but we might also have a BRL, which would branch to a register, but also link to a register. And that would be the true analog to Jailer. Leg V8 doesn't really have a halt instruction. That's because of operating system things. Don't worry about that. When you see the end of a file for Leg V8, that's essentially the halt. And we do sort of have no ops, but no ops are going to be generally pointless as we think right now. We'll see their true use later in the course, so don't really worry about no ops. So let's look at some of these practice problems. So real basic. So let's say that we want to put 12 into some register X11, and we can do that with a move instruction, and specifically a move Z. So I'll introduce you to the move Z instruction. So I showed on the last slide, move Z 0, 0 is out of register. Similarly, move Z with some other value will place that value into the register, provided that this value is, I believe, no larger than 16 bits. So on the next line, we can do the same thing. So move Z, place it into X12, 71. And 71 is a number that fits in 16 bits. So now, if we wanted to left shift X11 by 16, we have a dedicated LSL instruction, and we're going to place it back in register 11. That's what the left shift equals is doing here. So do it X11. This is our destination, by the way, which is inverted from LC2K, because in LC2K, the destination is on the end. So we do LSL, X11, and 16. Then we could do an AND operation. Once again, this is going to do the AND operation in place. So we'll put it back into register 12. Our source will be register 12. In LC2K, we would have to load this mask, but because we have immediate operations, we can just do an AND I, where the I stands for immediate, which is like a constant, and then we can just place in the value. The value of XFFF is 4096. So I'll just place that for now. I think technically there's a way to put it in hex for ARM, but we're not going to worry about that. I don't think it would be counted off on the exam for putting hex or binary into these values or into these immediate places. And then finally, looking at this last one, we're not using constants anymore. We're not using like 16 in FFF or 12 or 71. So we are going to do a register operation. So we're going to do an OR, which we have. And let's see, we're going to place it into A, which was X11. We're going to do it between A and B, so between X11 and X12. And that would be our answer. So if we were to put an I after the OR, that would be incorrect. If you were to miss the I from the AND I, that would be incorrect. So that's some basic C to ARM code. And unfortunately, my next slide has all that. So I'm just going to clear most of this before we move on to problem number 5. But I am going to leave the idea that our what do you call it? Our first register in our arguments for ARM is going to be our destination. So I'll just move that over here. Remember that that's the destination. It's different from LC2K. All right, so you want to take this one?
Yeah, sure. So this is going to be similar to what we worked through in LC2K earlier, where we were converting from C to assembly. So let's go ahead and take a shot at doing that. So one difference that we haven't really touched on yet is how labels work in ARM. So labels in ARM occur on the left side as well, but you're going to have just like a semicolon for it. And then you have whatever code applies there. So the only difference really is that semicolon that you're going to see. Okay, so this is going to be similar. We're going to perform a while loop. So we're going to be wanting to check that condition. And then within that, we're going to have an if else state. So let's attack the while loop part first. So this gets into how to perform branching in ARM, or more accurately in ARM like V8. So the way we do that is with this instruction called CMP, like compare, right? And CMP takes two arguments, right? So you take either two registers, or it could take a register and an immediate value. So in this case, the two values that we want to compare are x1 and 0. So the way we would do that is we would accept register 1, and we would accept the immediate value 0. So once we've done a compare, it calculates a bunch of flags internally. And at that point, we can execute branching instructions. So unlike earlier in LC2K, where you had the BEQ, where it would compare and then immediately execute all in one instruction, in ARM, those instructions are kind of split up. So at this point, if I wanted to check if x1 is not equal to 0, or more accurately, if I want to check if they're equals to each other, I could do a branch, right? So that B indicates that I'm going to execute a branch instruction, and then I specify the type of comparison that I want, or what I want to check for. So if I did B.EQ, that means I'm going to branch if equals to. And the only parameter I give it is the label to which I want to jump. So if x1 is equal to 0, then I'm essentially just done with my loop. And so at the very end of my code, I might have a label called done, right? And remember, we don't have a halt or anything, so it's essentially just we're gonna leave that blank. And so I would put my label here. So the parameters, what this branching instruction is comparing, is the values that were in the last comparison. So the only comparison I have right now is CMP x1 to immediate 0. And so any sequential or any branching instructions that come after it are going to look at the most recent compare. So this allows us to essentially break out of our loop once x1 does equal to 0. So now let's look at the next part that we have to check, or the next condition that we have to check. So we want to execute this code if x1 is less than 0, and this code if x1 is not less than 0, it's greater than or equal to it. And so the way that we can do that is, well, it looks like the two values that we're comparing are x1 and 0 again. So note earlier when I was explaining comparisons or mentioning how branching instructions work, I said that you look at the most recent comparison. So in this case, I don't need to perform another comparison because my last CMP was with the parameters that I'm comparing again. However, what this is going to affect is like what instruction or what type of comparison I'm executing. So here we want to perhaps run x1 minus minus if x1 is greater than or equal to 0. So note that I flipped essentially the operation that we're doing because I could totally do LT, which is like less than. But the reason I'm doing GE as opposed to less than is so that we can, and you'll see this once I'm done in just a minute, it will kind of keep the code in order. And so we don't have to flip the order in which the code appears. So if I did a b.ge, so I'm going to branch to a certain label, And let's call this like the, well, the operation that's being performed here is a decrement. So let's make a label for a part of the code that's just going to decrement. And we're going to jump to that point in code if it's x1 is greater than or equal to 0. The other part of code, I'm going to label this, even though it really doesn't need a label, is going to be the increment operator. So if we don't jump, we are essentially going to want to execute this line of code. And so what we're doing here is we're adding 1 to the register 1. And so the way we do that, well, we can use 1 as an immediate value. So the operation that we would kind of want here is add I. Right. And so again, the first register is going to be the destination register. So I'm incrementing. So my destination is also going to be register 1. The source register, or one of the parameters to the addition, is also going to be register 1. And the value that I'm adding to it is going to be just the immediate value 1. So note that the I here corresponds to the fact that I have an immediate value. Well, once I've executed this increment, then I want to go back and check my condition, just like earlier. So earlier in LC2K, we had that line called BQ, and then we were using register 0, 0, and then the label that we wanted to jump to. Well, in ARM-like V8, we have a slightly simpler instruction, which is just B. And so that's a non-conditional branch. So it's going to act just like BQ 0, 0. And we just specify the label that we want to jump to. So we're going to jump all the way back to the start of the loop. So let's do the decrement part now. So we've successfully done at this part of the code. Let's do the decrement as well. So if we jump to the decrement, then we're going to want to subtract 1 from register 1. So we have an instruction called sub immediate. And the parameters are going to be the exact same as the add instruction. We're going to have x1, we're going to have x as the destination, we're going to have x1 as one of the sources, and because we want to subtract the immediate value 1, this will be our last parameter. So once we're done decrementing, we still want to loop back to the, or we want to jump back to the start of the loop. So we very similarly can do loop. So essentially, what we've accomplished here is we perform all of our condition checking, right? Both of these comparisons. I could color code them. So we're going to perform both of these comparisons in this code right here. And we've split up our code so that our increment, which corresponds to this code right here, will execute if the greater than equal to is false, and our decrement will execute if it is true. And once we meet the condition that that x1, register 1, is equal to 0, we're going to jump to the label done, at which point we've kind of reached the end of the file. So we're done executing our instruction.
All right.
Let's clear my notes.
Yep. There it is.
Yep. And so the one thing, and I mentioned this earlier just quickly, but instead of using greater than equal to, as I used in my solution, you could also use less than. The only result would be that you would kind of switch the decrement and increment operators. The reason I chose out of preference to do greater than or equal to is that you can see how like the code lines up with the blue part kind of lines up with the blue part, and like the red part comes after the red part. But if you want to do it as such, you'll note that I had to flip the operator. I had to switch the operator that I was doing. So that's, both options work. It's just something to consider.
All right, let's move on to problem 6. So we have some ARM code that's, wow, pretty confusing to look at first. But we're going to translate it literally, and then we'll see if we can pick out some things to actually make it useful to us. All right, so this is very easy to do just straight up. So I'll start with the top. So let's say x20 is 1, x21 is 1, x19 is 0. And by the way, remember that this is hex. So we were saying earlier, there's a way to do hex and arm. That's how you do it. So now let's look at this. So I see a branch. It's going to go down to the bottom and do a comparison. And then if that comparison checks out, it'll come back up. So if that comparison is false, it'll just keep going. And so that tells me that it's like a while loop, like how we were showing earlier. So it's not a do while loop. This is not guaranteed to run once, but it is like a while loop. So while, and then let's look at our condition. So while x19 is less than 63, which is, geez, I don't know what that number is. I'll just do it literally for now. So while x19 is less than 63 hex, we're going to do some stuff. Let's look at what we do. So we're going to add x20 with x21 and store it in itself. So x20 plus equals x21. Then we look at our move. So that's essentially copy. Oh, and I completely forgot a copy up above. I'm going to have to go back for a second. My eyes just did not see that first move. So make sure to not make that same mistake. Okay, so going back, x22, that's our destination. So x22 equals x20. x20 plus equals x21, semicolons. And then x21 equals x22. And then we're going to increment x19. So x19 plus plus. All right. So this looks pretty confusing as is, but that's technically correct. Let's see if we can figure out what was originally written. And I'll do that by erasing and then showing you that. All right. Let's look here. So we start off with some ones and zeros. X19 is going to be an increment of some sort. So I'm going to go ahead and convert this into a for loop. So for x19 equals 0, semicolon, x19 is less than, and I guess it gave us the number, which is 99. And then we're going to plus plus x19. So plus plus x19. All right. And let's see what else. So we've done essentially this line now. We've taken care of this line, and we've taken care of this line. So let's see. So we start off with some ones. It looks like we're going to preserve one of the ones. So essentially, this value is going to go down here in the end. And then in the meantime, we're going to modify that value. So it looks like x22, it's not going to be read somewhere else. So I'm going to call that temp. So temp is x20, x20 plus equals x21, and then x21 equals temp. And of course, we have our initializations. So the actual answer, if you can't tell what this is doing, this is the Fibonacci algorithm. And that's pretty hard for me to see, but we can still get something that's pretty close. I think the only difference here is my register names. We could also still keep this as a plus equals if we wanted to. They renamed x19 to I. And then I personally would still call this temp, but that's just me. So this will calculate Fibonacci numbers in sequence, which I think is pretty confusing. You probably don't need to know how to do that. But trying to get to this point, converting the while loop to the for loop, and making sure you have your initializations is probably the thing that you need to know. All right, so you want to take the Endianness questions? Let's see, is Sunny still here? Oh, he's muted.
Yeah, I
There
didn't realize I was muted. There we go. I'd gladly take this question. So one of the big things that we mentioned earlier as the differences between ARM and ARM like V8 and LC2K is the addressability, right? We talked about how in LC2K we use what's word addressable. So when we add index a place in memory, we're kind of accessing every 4 bytes. Whereas in ARM, we're going to be using byte addressability, which means we're going to be accessing each byte location. And that's going to affect a couple of things. Also, recall from our last discussion or earlier in lectures, we talked about Endianness, which was, I guess, the order in which we represent bytes. So in big Endian, we have the most significant bytes. So if we had an integer that was of size 4, the bytes that go to the leftmost side are going to be the bytes that go in the lower addresses. Contrarily, little endian is kind of going to be the opposite of that, where the bytes that that are most to the left, that have the most significant values, are going to be at the highest addresses. So if I was looking in this range, for instance, in big endian, I might, if this was a 4-byte integer, my integer might look something like this in memory, or this is going to be the value that it's going to take. All right, so let's go ahead and take a shot at this question. So the first instruction that we're executing is a move Z, and we are putting inside register 1 the immediate value 1000. So in addition to kind of like our memory representation that we're going to have over there, we're going to store all of our registers right here in the middle, right? And just overviewing all of the commands, we're really only going to have registers X1 and registers X2. Okay. So it looks like initially we are assigning the immediate value 1000. Cool. We're going to assign the value. I call it hex 1000. I really mean hex 1000, which I think is the big number. Regardless. So that's the value that we perform. So regardless of what was inside register 1 before the operation, it was all cleared out and turned into zeros and then assigned. So then in the second operation, we're performing an add instruction. It's an add I. So we're going to add an immediate value to register 1. So the destination register, again, is that first register. So we're going to be, register 1 is going to be assigned to the sum of whatever was in register 1 and the immediate value 4. And so we're going, so if we add 4 to this, then the value that we're going to end up getting is 1004. Awesome. So far, we haven't actually interacted with memory at all. So big endianness, little endianness hasn't really played a significant effect. So then finally, we're going to interact with memory. So elder H, or ladur H, or however you choose to pronounce it, is going to be an instruction that loads, so that H at the end signifies a half word. So a half word is going to be 2 bytes. So essentially, we're going to be loading 2 bytes from memory into register 2. So our destination register is 2, and the location we're loading it from is going to be the value inside register 1 plus 0. So the value inside register 1 right now is 1004. So that's going to point right here. And we're going to add 0 to that. So it's going to stay at that location. And we are going to load 2 bytes starting at that address. So the memory range that we're looking at here is these 2 blocks. So this is where endianness plays a role. So recall that for big endianness, the lowest address has the most significant value. And so when we load this into register 2, well, the result that we're going to get is that the 77, the first byte is going to be on the left side, and the second byte at address 1005 is going to be on the right side. Awesome. So then that's done with our third instruction. Now this fourth instruction, we're going to store we're going to take the least, so it's a stir B. So that B refers to a singular byte. So we're going to take the least significant byte in register 2, and we're going to assign that to the place. We're going to put that byte at this location in memory. So recall, this is going to be the same location that we just saw 1 second ago. So it's going to be where that yellow arrow is pointing. And so we're going to take the least significant byte. So recall, this is going to be, so this is going to end up being this byte right here. And we're going to overwrite the value at that the location with that value, so that this 77 is going to end up getting overwritten with the value hex 50, and that's because that's the least significant byte there. So that is what is accomplished at that instruction. So that last instruction, we're going to store an entire word. So recall, a word is 4 bytes. So we're going to take the least significant 4 bytes. So recall that, even though I don't have like 4 bytes clearly displayed there, everything else is just going to be, we're going to assume are zeros. So we're going to take all 4 of those bytes from register 2, and we're going to put that at this spot in memory. Well, where is that? Well, that's going to be the value of register 1. So recall that's going to be 1004 minus 4. So we're going to go back 4. And so it's going to point to the start of like the memory address at 1000. So starting here, we are going to overwrite all of the memory. And so this again is where big endianness comes into place, where we take the most significant byte. So the most significant byte is going to be right here. And so that most significant byte is going to be the first value that goes in my memory addresses. So my memory over here, it's going to be overwritten as 00. The next most significant byte, which is also going to be a 00, is going to be written in the next lowest memory address. The third, or I guess the third memory address is going to be written with the 77. And the least significant one is going to go here. And so we've successfully now completed all of our operations. So the reason big endianness and little endianness matters is because it affects the way we extract bytes out of our memory. So if I clear my notes right here and I Yep. So that's going to be the solutions that we got. Awesome. Nate, Mason, do you want to take 7B, or I'd be happy to take it as well, whatever you prefer.
Yeah, I'll go ahead and take 7B and 8 and finish this up here.
Awesome.
So yeah, so I think 7B is going to be easiest if we remember what we did from 7A, and then we can make it go really quickly. So first step, we're going to set x1 to 1000 in hex. I don't remember what the exact number that translates to, but we have a memory address, it's 1000. We're going to be using that for offsetting. And then now we're going to update it to be 0x1004. All right. So once again, we're doing a ledir H, exact same instruction. It's going to be stored in x2 from whatever location is currently in x1, which is 1004. So we have 1004 that Sunny pointed to earlier, but now we're doing this in Little Endian. And so there's a couple things here. So first thing is that we're going to have our bytes reversed, right? So before we had 7750, now we're going to have 5077. And it's Little Endian because this last byte, the 77, has the littlest address, 1004. So 1004 compared to 1005. And of course, we're still doing a half word. So we're going to load just 2 bytes. Now, you might think that in reversing the order, we would add a bunch of zeros to the end. That is not what we're going to do. After loading our 2 bytes to the rightmost or least significant bit fields in our register, we are still going to keep our leading zeros on the left. So we have a bunch of leading zeros on the left. All right. And now we are going to do a stir B once again to that 1004 address. We're going to take the least significant byte, which is the 77, the rightmost byte, and look at that. So a byte-sized loader store is going to behave the exact same way in Little Endian or Big Endian. It's really only when you mix these different types that the behavior changes. So here we're mixing half-word loads with byte stores and word-size stores. If you keep everything consistent, so if you had only loads and stores for half words, the behavior would be the same. So Endianness really only matters for types where we're going to be mixing our loads and stores. So your C code, as long as you're not manually doing that, which is really hard to do anyway, you don't even have to worry about this. And then finally, we're going to store a word to address 1000. And we're going to know that 77 has a little less address, so it will be 1000. So we'll overwrite this with hex 77, then hex 50. And remembering those leading zeros, we're going to overwrite the zeros here this time, when before they were in addresses 1000 and 1001. So now x2 is this, and x1 is still 1004 in hex. And so that's our solution. Yep. Right. So that's the difference between Little and Big Endian. For our last thing, we're going to look at a little bit of structs. We're going to do what's called struct alignment in lecture. We're not going to cover that in discussion, but you do need to know a couple things about structs. For this problem, we're going to assume correctly that a struct is going to look like this. So it's going to have 2 64-bit integers. Those are 8 bytes, and they're going to be at adjacent memory locations. So they're going to be right next to each other. If we have a pointer to the beginning of the struct, let's call it x, then this int real will start at x plus 0. And because real is 8 bytes, the next member, imaginary, has to start 8 bytes later. So x plus 8 is where imaginary is going to be. And we're going to have an array of structs. So it's going to be 10 reals and imaginaries alternating. And that's how this is going to be. So let's look at our stuff here. So we are trying to move a real part from, I guess, some given integer b plus into n. And then we're trying to store that new value of b, that imaginary part, into n, which is x5. So let's start looking at this. So first, we have to do our pointer arithmetic. So we have array, a pointer to the beginning of array, which is in x0. We have b. So remember that when we do our indexing, so array at b, this is equivalent to dereference array plus b. However, b is an integer. And if b is 1, for example, we wouldn't want to access, let's say that r is 0x1000. If b is 1, we would not want to access 1001. That'd be bad. We would want to access the, I guess, second struct in this array. And so at that point, we need to multiply this 1 by the size of our struct. And our size of our struct is 16. This is 8 plus 8. And so we are actually going to take 16 times b when we do our operation here. We don't have to do a multiplication explicitly. We're just going to left shift by 4 since that's the same as multiplying by 16. So we're going to take B, which is, let's see, x1, and left shift it. So LSL x1, we're going to store it back. Actually, I'm going to store it in a new temporary register to make sure I don't mess something up in case we need to use that B later, which we will. So we're taking, I've reversed my operands again, which I always tend to do. So we want to store this into x1, the left shifted version of x1. We'll store that in x2. And then we'll just left shift by 4. Okay, so now we have B times 16. We need to add that with array, which is x0. So I'll do an add x, I'll call it x2. How about x2? I'll just reuse that x2 and we'll add x2 plus x0. So now we have this here without the dereference, I suppose. Right. And then we're going to do our final offset since we'll actually need to add 8, or actually I'm getting ahead of myself. Never mind. We're going to be able to just use this calculated address to get the real part. Later, we'll have to add 8 in order to access the imaginary part. So I'll just do, let's see, this is a 64-bit, so I'll have to do a full ladder, which will load a full 64 bits from an address x2, and they want me to put it into x4. So I'll do something like that. All right. Now I need to remember to increment B because this is a postfix increment. So I'll do an add I with x1 and again x1 and 1. And now we're going to do the exact same thing. We're going to left shift x1 into x2 by 4 to do our pointer arithmetic. We'll have to add that result to array. I'll just store it again in x2. And then this time when we do our ladder into x5, we will have to use 8 as an offset in order to access the imaginary part. And so that's what that would look like. I'm going to go ahead and clear this. Not all of it though. I want to keep a lot of this actually. So remove that. And then I will show these the actual solution. There we are, while I'm still erasing. And that you will see that they use different registers in the solution. Same thing. Right. So that's everything that we have for today. Join us next time, and good luck on the projects and homework.